What's up, math scholars and math haters? This is Mr. W. We are continuing with the normal distribution and moving on to something called the empirical rule. Now, if you have been in science class, you might have heard the word empirical as something that can be proven, and this is the empirical rule because it can be proven that all of this is true just by doing some quick analysis of the normal distribution itself. But I still have the IQ scores distribution from the first video. Mean is still 100, standard deviation is still 15. But I have added these lines down here. Now this will let me go over the formal way that people think about the empirical rule, but there is another way that I think is a little bit easier. The formal way to think about the empirical rule deals with just three numbers: 68, 95, and 99.7. All of these numbers are percentages, and in fact they are percents of data between -1 and 1 standard deviation for 68, -2 and +2 standard deviations for 95, -3 and +3 standard deviations for 99.7. It's a nice easy thing to remember three numbers. Individual problems, though, are going to ask you to look at different parts of this between standard deviations, or less than -3, more than 3, and even add some together. So it is for that reason that I think that this is not necessarily the easiest way to think about this. So I'm going to erase these. And I'm going to draw something else. All that these little lines are doing will show us exactly what percent of data is in between each of these parts, or in the case of above 3 and below -3, just off on the edges of the little tails there. Now you can actually do the math on this for yourself, but I hope you will take my word for it that the numbers we end up with are from inside to outside. 34% of data is between 0 and 1, also between -1 and 0. 13.5% of data is between either 1 and 2 standard deviations, or -1 and -2. Over here we have 2.35% of data between 2 and 3 standard deviations, also between -2 and -3. And finally, that leaves a measly 0.15%, and this is not like 0.15 that I accidentally put a percent on. This is 0.15 of 100th of the data for each of these little tails. I do think that remembering these four numbers, 34, 13.5, 2.35, 0.15, going from inside to outside, makes the math a little bit easier, even if the numbers themselves are more difficult to remember if you can only pick one set. If I could only pick one set, I would pick these four. That's just me personally. The other way might work better for you. But now we need to actually think about using this. A big part of working with normal distributions is finding percentages of people between different numbers. There's a more complicated way to do this that will let us look at data points that aren't right on the lines representing the standard deviations, but we'll worry about that in another video. For right now, we are just going to worry about finding the percent of people with IQ scores between each of these ranges. And I'm going to have to scooch this board up and down a lot, so you might hear a lot of creaking, unfortunately. But to start with, we have 100 and 115. Now 100 was our mean, 115 was 1 standard deviation, so thankfully, this problem just has us write down a number that it already gave us, 34%. 34% of people have IQs between 100 and 115. Down here, we have 100 and 145. Now this will have us go from 100 all the way over to 145. So I need to add 34 plus 13.5 plus 2.35. And if you add those up, you can use your calculator to check me on this, but I am very, very sure that this ends up being 49.85% of people, which makes sense. Because if you look at the actual distribution, 100 to 145 is almost all of the right half. So it would make sense for the percentage of people with those IQ scores to be about 50, or about half. Now we have 85 and 145, which if we look up here, that takes us at 34, 34, 13.5, and 2.35, We add all those percentages together, and we end up with 83.85%. Next question asks us about between 55 and 85. That's 13.5 plus 2.35 gives us 15.85%. It's a little cramped, so I have to move my percent symbol down a little bit. These questions do give us a little bit more of a trickiness factor. Only because if we do see a problem like less than 130, the percentage of people with IQs less than 130, we start at 130 and we just have to keep going all the way over here, adding up everything as we go. So this would actually give us, if we add all these together, exactly 97.5%. And finally, if we're looking for more than 100, again, we come back up here. We start at 100, we add 34, 13.5, 2.35, and the 0.15. I think the trickiest part of these problems is just remembering that the 0.15 over here is the very, very last one. There's nothing else in between, or it's not like it's between 3 and 4 or anything like that. It starts at 3 and it goes all the way and encompasses all the rest of the data. But if we look at this, we can see that 100 is the mean. It's also the median, which means exactly half the data should be above this point. And if we add 34, 13.5, 2.35, and 0.15, that will, in fact, give us exactly 50% of the data. Now, I do want to do this with the pizza delivery example as well, in large part just to help you see that no matter what our mean or standard deviation are here, these numbers in between each increment of one standard deviation, or on the tails, stay exactly the same. So if we're going to look at this distribution, where the mean delivery time was 25 minutes and the standard deviation of those times was 8 minutes, giving us adding 8 as we go to the right, subtracting 8 as we go to the left, like we covered in the last video. If we're looking for the percent of deliveries between these two sets of times, then we'll have another less problem and more problem over here. Our numbers are exactly the same. So between 9 and 33, we're still just looking for our 34, 34, 13.5, which will actually give us 81.5%. Between 1 minute and 41 minutes, that's between 1 and 41, so we have a 2.35, 13.5, 34, 34, 13.5, and that is going to give us 97.35% of our data, or of our deliveries are going to be between 1 minute and 41 minutes. And once again, if we see a less problem or a more problem, the trickiest thing is just to remember that this tail over here is everything to the left of -3 standard deviations, or everything to the right of +3 standard deviations. So for less than 17 minutes, we're just going to add 13.5, 2.35, and 0.15, and it will give us 16% of our data. And then for more than 17 minutes, there's actually 2 ways we could find this. I'll start by just picking the way where we add up everything. 34 plus 34 plus 13.5 plus 2.35 plus 0.15 will give us, 84%. We could also get that by thinking through, okay, 100% is everything. So if I have the percent of deliveries less than a particular time and the percent more than a particular time, I should be able to get 100% when I add up what's less than and what's more than that particular time. Now, this does go against what you may have thought about numbers before, even maybe in a statistical context where you have to count 17 as its own thing. But thinking about the idea of an area under a curve, and this is getting a little bit more into calculus, just that one number represents the tiniest sliver of data. It represents essentially 0. But all these little lines, and if I were to actually draw them, I'll go ahead and do that here. We have a whole bunch of little lines under this curve that are grouped so close together that they actually come together to give us the different percentages of data that we're dealing with. So just to reiterate, we do not have to count the number itself as something, even if we see less than and more than, because in statistics language and the calculus that this idea comes from, it basically represents nothing. So I hope that that wasn't too conceptual of a way to end this, but but nonetheless, I hope that this helps you on whatever assignment that you're on, whether or not you are my student.